We're putting neurons on electrodes. This allows us communication with neurons, so we can send them signals, electrical, and we can also read the signals from neurons.
Somewhere in a lab in Switzerland, a group of researchers sent an electric signal pulse to a network of living neurons. And guess what? The neurons responded. They adapted. They learned. And for the first time, a computer made of living cells began to behave like something far more powerful than any line of code.
And the whole idea is to have a processor which will be living neurons. So like today we have silicon processor, tomorrow we will have a bioprocessor. That will be living neurons processing information.
And if I may ask, what is the average life of a neuron cell?
It's around 3 months. Our success, I think, was 7 months. We put it in our recent newsletter, but that was outlier. Most of the time it's around 3 months. The neurons are good in processing efficiently very complex information. So this is what brain is doing very well, and we think that biocomputer will have the same properties.
Remote access to living neurons is a bold idea, one that requires not just scientific sophistication but ethical architecture as well. And I'm sure listeners will want to know how you think about safety, oversight and integrity.
I think safety is not a big problem. Actually, the biggest danger is that neurons will get contaminated. It's a big challenge in biology in general, and that's something, let's say the safety of neurons, that's the biggest challenge. Because they don't have immune system, of course, so that means that any bacteria or something can be, or fungi, can be a huge problem in the lab, and then the cells die.
Today, we are joined by someone standing right at the center of this moment, Dr. Ewelina Kurtys, neuroscientist, biocomputing innovator, a leading voice in the team bringing the neuro platform to life. Evelina, welcome to Drug Diaries. Before we jump into today's episode, I just want to say something from the heart. Over 93% of the people who watch this podcast regularly haven't subscribed. And listen, I get it. Life is busy. You click, you watch, you move on. But if you've ever felt like this show brings you value, if it has made you think, sparked a new idea, introduced you to something inspiring, then I have a small favor to ask. Please hit that subscribe button. It might not seem like much, but to me, it means everything. This podcast has always been a labor of love. No sponsors, no script, just honest conversations with people trying to make a difference in the world of healthcare. And your support, your one click, helps me keep doing that. It helps more people discover these voices. It helps this community grow. So if you're here, if you believe in this, please consider subscribing. Thank you for being here. Now let's get into the episode. There are moments in science when the world quietly shifts beneath our feet. Not with fireworks, not with bold announcements, but with a small dish, a cluster of human neurons, and a signal that should not have meant anything at all. Yet it did. Somewhere in a lab in Switzerland, a group of researchers sent an electric pulse to a network of living human neurons. And the neurons responded. They adapted and they learned. And for the first time, a computer made of living cells began to behave like something far more powerful than any line of code. Today, artificial intelligence consumes more energy than entire nations. Silicon chips are shrinking to their physical limits. Data centers are beginning to sound more like industrial plants than servers. And while the world makes predictions about the future of AI, a different kind of intelligence is quietly emerging. Not artificial, not digital, biological. A new frontier many people have never heard of. A frontier where computation is not built but grown, where intelligence emerges not from transistors but from cells, where the next revolution in computing might not be coded, it might be cultured. And that brings us to Final Spark, a company that decided to stop asking what AI will do next and instead asked a different question. What can living neurons do when you give them the right environment, the right stimulation, and the right problem to solve? They built the first remotely accessible biocomputing platform on the planet. And the story behind it is of curiosity, of courage, and of reimagining the limits of what intelligence can be. Today, we are joined by someone standing at the center of this moment, Dr. Ewelina Kurtys, neuroscientist, biocomputing innovator, a leading voice in the team bringing the neuro platform to life. Her work sits at the edge of neuroscience, technology, and philosophy. It challenges what we believe intelligence is, how computation might evolve, and what it means to build technology that does not just process information, but adapts to it. Evelina is here to take us inside the world. So before we begin, I invite you all to listen with curiosity, with imagination, and with the awareness that the conversation you are about to hear might change the way you think about the future of intelligence. Evelina, welcome to Drug Diaries.
Thank you very much. It's a pleasure to be here.
Thank you. So, Evelina, every time I try to explain your work to someone, I see the same look, a kind of disbelief mixed with fascination, because for most people, the idea of living neurons doing computation feels like something from a film, from a sci-fi movie, not a lab. But your journey into this world started long before the public ever heard of biocomputing. So, when did the story start for you?
So I did a PhD in neuroscience. So I was definitely on the biology side in the past. But later, when I moved to industry, I started to work on artificial intelligence. And I became really fascinated with that. And on one of the conferences about artificial intelligence, I met the founders of Final Spark. And I became really fascinated with the project because it's at the intersection of two fields which are interesting for me. So neuroscience and
Mhm.
engineering and artificial
Right.
intelligence. So we believe it's a future of artificial intelligence.
It's excellent. And I often feel that people who end up working on frontier science were shaped by quiet moments long before the breakthrough.
Yes.
Small curiosities, questions no one else noticed. I'm curious about the seed of curiosity in you. Before Final Spark, who was Evelina and what shaped your curiosity about the brain?
No, I think I'm always the same person, and
Right.
I was just always curious. I don't know. I think it's just some kind of questions are more interesting for you than others, and
Yeah.
I think it starts with in childhood, and just somehow some things are more exciting than others. And I don't know why. I always wanted to know things about nature and about, let's say, biology and human body. And later, someone gave me an advice that when I was thinking about my PhD, then that I should think about part of the medicine, which is or medical science, which I find the most exciting. And then I thought, of course, it's brain. So I
Yeah.
aimed for a neuroscience.
Right. And was there a moment when you realized neurons outside the human body could compute?
No, I didn't actually. I
Right.
only after I talked to Fred Jordan, one of the co-founder of Final Spark, he told me he wants to build a computer from living neurons. So I thought he's either a genius or crazy.
Yeah.
And if a genius, then I want to work with them.
Right.
Because it was
And what?
very unusual, and I can tell you that biologists, I think, wouldn't think about that because that
Yeah.
idea comes more from engineering. Because Fred and Martin, the founders, they have PhD in signal processing, so and they have also experience in engineering, so not only mathematics but also coding and everything. So this is more idea of this kind of people, how to build a machine. A thinking machine, that was the dream which they had, and they
Right.
arrived to biology because they found that it might be the best way to think, to build a thinking machine.
Mm. Right. And Evelina, whenever I listen to your talks, there's philosophy behind the science, a view of intelligence and biology that feels bigger than experiments themselves. So I want to explore where the worldview comes from. And what do you believe about intelligence and the future of computation that most people have not yet considered?
Well, I don't know if what I think is what is new for other people, and they didn't consider this. I cannot say, but I think that intelligence is processing information, and of course you have to always distinguish. I think we now have a problem with that between maybe consciousness and human traits and machines, and I think
Mhm.
because machines become better and more intelligent, like for example ChatGPT, can talk to you like a human almost. It's now
Yeah.
really excellent, and I think we start to this difference starts to blur, and we might try to assign try to consider AI as human, and I think this is already starting, and I unfortunately I see also this trend that there are some startups already who are building like kind of companion friends or even boyfriend or girlfriend, which is AI,
Yeah.
which I personally I find it terrible, but because I am so old that for me, I think in our generation is still not acceptable, but I think that new generation, when they're born and they've seen AI since the beginning, I think they will have different view, and for them maybe it will be normal. So I think it will end up like that there will be many people having friends, or some even relationship with AI. But that also brings another problem that some people start to believe that AI is conscious, which I personally don't believe. However, I'm not philosopher, so maybe I have to respect the fact that still, there is 100 years of research of many philosophers, and some of them believe in consciousness, other not. So, okay, the field, of course, is divided because it's something we cannot measure. We can only be sure about our own consciousness.
Yeah.
So it will always be based just on reasoning, and everyone can have different. So yeah, I think it's a controversial topic, but I think it's a mistake we are doing today when we see intelligent AI. And also when people hear that we are working on living neurons, they also think, oh yeah, then they are thinking they're enslaved in the lab or something like that. But just because it's a tissue, these are living cells, I don't think they are conscious. But it's interesting discussion, which we sometimes have about AI in the public.
Right. Right. I was going to ask you about your views on consciousness, but you just mentioned that not all matter is conscious, right? That's
Yeah,
your
that's
view.
what I believe. Although
Yeah.
yeah, it's still belief because it's never science. When you talk about consciousness, you cannot be scientific. But
Yeah.
when
I
we talk
think.
about AI in general, I think maybe just to mention, I think the most important problem which we have today, or will be soon even more important when AI is more intelligent, is the alignment. So I think we should focus more on that instead of inventing stories about enslavement. I think we should focus on something what is real issue, which is how to make sure that AI is aligned with us. Because I think today it still works very well. Like, when you interact with LLMs or something, they are always like on your side. But still, I think it's dangerous that one day, and this is also raised by some philosophers and some experts, also engineers in the field of AI, that one day it can be dangerous that AI can do something against us and it will be more intelligent than us. So we might be a little bit in trouble. So I think that's much more important. That's actually the most important problem now in AI, how to make sure that it is for good, not for bad.
Very well said. I agree.
Yes.
And Evelina, before we go deeper, I want to pause and take a breath because what you do is so new to many people that I'm sure a lot of the people may never even have heard of the term biocomputing. And this is one of those moments where simplifying the core idea can change how listeners experience the entire conversation and entire episode. So, how do you explain biocomputing simply for new listeners? How would you explain it to a 12-year-old?
Yes, sure. So what we try to do is we try to build computers only with living neurons, so the same as we have in our brain. And we do this by putting neurons on electrodes, and this allows us communication with neurons, so we can send them signals, electrical, and we can also read the signals from neurons, because neurons have spontaneous activity in form of changes of voltage. And they also can be stimulated, so they also might respond differently if you stimulate them with current. And the whole idea is to have a processor which will be living neurons. So like
Right.
today we have silicon processor, tomorrow we will have a bioprocessor. That will be living neurons processing information. So
Wow.
that's the objective which we aim for. And the reason why we do this is because neurons are 1 million times more energy efficient than digital computers. That's the reason. So we try to solve the problem, which is now emerging, that artificial intelligence is using exponentially increasing amount of energy. And in the future, we might have a problem with that. And also AI might become at some point very expensive, maybe to some people too expensive.
And pardon my ignorance, and sorry for asking a silly question, but where do we get the neurons from?
And that's a silly question. So we get them from a human skin. So
Right.
there today you can buy actually commercial. It's very standard process used in many labs. For biomedical research, you can buy stem cells, which are derived from human skin. And these stem cells you can use to produce any type of cells, theoretically, any type of cells which are in the human body, and including neurons. So we produce neurons from in such a way, from stem cells which are derived from human skin.
Right. So if I were to operate a very basic computer,
Mhm.
uh, I'm just trying to get the scale of this. So, how many neurons do you think I would need to run a small computer?
Many. I think really a lot. But today we have prototypes, which are very small. They consist of around 10,000 neurons each and around
Right.
half millimeter diameter. And these are the prototypes of biocomputers. And we just use it for testing. But of course, we aim for scaling. In the future, we would like to scale for a huge amount, even 100 meters long. Because, in the nature, we are constrained that, okay, our heads cannot be too big. So our brains are small. But if we produce neurons in the lab, maybe we can
Right.
produce much more. And we can build something much bigger.
And do you think, sure, and do you think these neurons have to be human derived neurons or they can also come from animal?
I think, hard to say, I think we will have to check in practice. For now we do such a simple stuff that it doesn't matter for sure. But in the future, it might be that if they do some advanced algorithm, that might be that only human neurons can do this. But, or maybe there will be even some genetically modified super neurons, because I think a lot of things in biology also go in that direction. So
Yeah.
it's hard to say. For sure, now it doesn't matter. We just do this. We use human neurons because it's easier
Right.
than, for example, taking primary cells from animals. Primary cells so means that you take them directly from the head, so you have to sacrifice animals. That would be difficult and expensive, and probably we wouldn't get ethical approval for that if we work on
Sure.
bio. Yes,
Right. So let's say if someone logs into the platform today,
yes.
what would they see? And what exactly are they interacting with?
So they would see they would see workspace to write a Python code.
Mm-hmm.
That's the way how we do experiments, actually. So it's a very engineering project. So
Right.
of course, cells, as I said, neurons are placed on electrodes, and
Mm-hmm.
electrodes are connected to digital hardware. So everything can be controlled through writing code in Python. And this is how we do experiments. We are just writing Python script. So we decide how we simulate the neurons when we collect the data, and we can also analyze the data. A lot of things it's automated in Python. So also doesn't matter if you sit in the lab in Switzerland or maybe you sit somewhere else. It doesn't really matter. Everything is the same. You just write Python code and it's executed in the lab and everything happens there. So yes, so today that's a possibility which we also give to universities from all over the world. We have some collaborators. We also have first commercial clients who pay us to get access to our laboratory. We have two types of subscription plan. It depends on how much you want to, how many experiments you want to do. And yes, today we are very proud of this, that there are so many people who use it, and it's all about coding. Yes, so it's all about Python. However, you need to have a knowledge about biology, because otherwise you might do a lot of things which totally don't make sense
Right.
from the neuron perspective. Yes, like for example, sending them too much current. If you send them
Yeah.
too much, you can kill.
Oh, really?
Oh yeah, because it's a biological tissue, so like with everything, there is some kind of dose optimal.
Right. And there's a sentence in your material that stayed with me. It said that neurons are not just passive tissues, they adapt, they
Yes,
reorganize, they
yes,
respond. And
absolutely.
that feels like beginning of intelligence. And I want to understand that process better. What does learning mean for neurons on a multi-electrode array?
I think neurons are intelligent. Yes, you have artificial intelligence, and you have many types of intelligence, and they can process information very effectively, as we know, because that's why we can talk, because our neurons are processing information. So there is definitely intelligence. It's just we cannot control this today in the lab.
Yeah.
So we don't know how to program neurons. We don't know how to do so that they do make them perform what we wanted. For example, you want to analyze text, or you want that to have conversation like today you have with ChatGPT on the digital processor. We cannot do this yet. But we know for sure that neurons are capable because the proof is a human brain. And we know, yes, neurons are very plastic and are continuously changing. So yes, when it makes sense, when there is some logic behind, there is that you can call this process learning. Because at the moment, what happens with neurons in the lab is quite random because we are still learning how to program them. But if we know how to do this consistently, then yes, you can call it learning. So basically they change all the time because of the interaction. So the same our brain. Our brain is plastic, and
Right.
every day we have some experience, even if we don't study the books, but still every experience is changing us. Yes, and the same happens in vitro. It's just that it's not controlled at the moment. And what I wanted to say, so basically the changes in the connection is a memory. So
Right.
actually that's also something different than between neurons and digital, that memory and processing is in the same place, because the connections between neurons are changed. So this is memory, and then the firing of the neurons, this is processing. So some information is processed. So that's different than in digital, where you have this separately.
Right. Right.
But this intelligence which you ask for, yes, this is actually spiking in time and space. So it's important when and where neurons are spiking, where in the tissue, for example, in our organoid or in the brain, the location and the timing. So that's also different than a computer 0-1 system. So this is
Right.
the intelligence, the spiking and the connections changing.
Sure. And I keep coming back to the butterfly demo, which I
Mhm.
watched somewhere. And because it is one thing to talk about neurons learning, but it's another thing entirely to watch living cells perform a task in real time. For many people, that is the moment the penny drops.
Yes.
And could you tell our audience a little bit about the butterfly experiment and the demo, and also explain how this works?
So when you put in the Google butterfly final spark, then you definitely can find it. It doesn't always work because we have limited resources, and this demo is connected to real neurons in the lab. So we don't always have capacity to run this. But if it works in the way that you have a web application with a so-called butterfly, which is actually the graphic butterfly, which is flying. You can decide in which direction it flies, but whether it flies or not is decided by the activity of the neurons. So that means that this web application is connected to the real neurons in our lab. So when you want that the butterfly will fly, you click, and then this click will send a signal to neurons in the lab.
Okay.
And then depending on the response, the butterfly will move or not.
That is so powerful to just imagine. And I've,
Yes,
I've seen that demo, and I would encourage everyone to at least try and log into the website and see if it works or not.
yes.
But
And
it's
also,
fascinating.
maybe I can mention, because maybe recently artists from Zurich, two students, they have done Luca Basbi and Eger Basil. I think you can find this also on YouTube, and we also put it on our website. They have done something similar, so they've made but it's physical, not a web application, but the same as Butterfly. So basically, they made a big painting, which is actually not a painting. It's just a kind of like canvas, which is moving. You can touch it, and when you touch it, the signal is sent to neurons in the lab
Oh,
in Verlin,
wow.
Switzerland. And then, depending on how neurons respond,
That's
the
amazing.
surface.
Evelina, I've noticed that whenever a new scientific field emerges, the gap between public imagination and scientific reality is enormous. And biocomputing is no exception. I think addressing misunderstanding head on helps ground the conversation. So, what do people most often misunderstand about the phrase living computer?
Quickly. Yes, so I think the biggest misunderstanding is that people might think that we are building a brain, human's brain in the lab, and that's definitely what we don't try to do this. Although organoids, which we are using, these little 3D structures of neurons, they are sometimes called mini brains, but this is not really, literary, I would say, because brain is much more complex than whatever you can build in the lab. And also, it's not our objective really to reproduce a human brain. We just use the same building blocks as in living brain. So I think this is, I find it the biggest maybe challenge for us to explain to the public perception.
Right, right. And how do you address concerns about feeling or consciousness in organoids?
Well, of course, we try to popularize our work, and we try to explain in very transparent way what we are doing, so that people can see. Also on our website on finalspark.com, you can see section live. You can see really the camera from our lab. You can see how neurons on the electrodes, how they look. How is the signal? But of course, we cannot do everything ourselves. We also put a lot of effort to get in touch with philosophers,
Mhm.
so that they help maybe. I mean, we of course don't want to influence them. It's not that we hire them. We just want to inspire them to do the research on biocomputing independently from us, and maybe this will also help because they can also think about all these questions, philosophical questions. If this is okay to build computers using living neurons, what is the public perception? Is there anything we should change? It's like every new technology is bringing new questions we didn't have before, and it's totally normal. And also we have to be ready that maybe we will need at some point adjust our technology so that it's ethical. So we are always open for suggestions because we want that our work is accepted by society, because of course otherwise it doesn't make sense, yes, if it's not accepted. We want to make good things, something against the society. So yes, it's very important, and we really hope that there will be soon some papers, maybe some thinking from philosophers, and that it will help us to answer this many questions also about consciousness, for example, or other things.
Yeah. Because indeed, remote access to living neurons is a bold idea, one
Mhm.
that requires not just scientific sophistication, but ethical architecture as well. And I'm sure listeners will want to know how you think about safety, oversight, and integrity. And how do you ensure safety and reproducibility with remote access to neurons?
I think safety is not a big problem. Actually, the biggest danger is that neurons will get contaminated. It's a big
Mhm.
challenge in biology in general. And that's something, let's say, the safety of neurons, that's the biggest
Neurons,
challenge because they don't have immune system, of course. So that means that any bacteria or something can be, or fungi can be a huge problem in the lab. And then the cells die. So this, let's say, a problem, I would say, when you talk about safety, is more about neuron safety of the samples, for me at least. And then if, what was the other thing? Reproducibility. That's actually a big challenge in biology in general.
Mm.
But with living neurons, if you want to program them in vitro, this is like huge challenge because it's not a stable system. So contrary to digital, it's a dynamic system. What does it mean? That means that if you put some input today, you get output, but tomorrow maybe you get totally different output for the same input. So this is a huge problem, and we have to find the logic behind this, behind this dynamics to make it reproducible. I think it's possible because our brain is also constantly changing, it's dynamic, but still we can be consistent with what we learned in the lab. We cannot do this yet to have this really consistent results. Sometimes we succeed with something, like for example, we succeeded with storing 1 bit of information, which is a great success for us. And this is something we've done many times. That's why we report this. But there are also many experiments we've done, which were very interesting, but maybe they worked once or twice. So then we don't report. So yes,
Right.
so it's still big challenge there, reproducibility. So yes, but it's because of the nature of the material. It's not because neural platform is bad or something, but I think it's really robust tool for working, and it's really working reliably. But the problem are the neurons that they are very very difficult to work with. So not everything is yet consistent. Yes, if you want
Right.
to program them, if you want to play with them, yes.
Sure. And if I may ask, what is the average life of a neuron cell?
It's around 3 months. Our success, I think, was 7 months. We put it in our recent newsletter, but that was outlier. Most of the time, it's around 3 months. And for now, we find that this is enough. But of course, in the future, we want to extend this time. This is the problem because, of course, in the lab, neurons are never in the, let's say, natural conditions.
Mm.
Because in our bodies, okay, it's perfect, let's say. But
Yeah.
when you put them in artificial intelligence, you put them in artificial environment on the plastic, or for example on electrodes. These are always materials which are not always biocompatible. So it's always a challenge how to make it more biocompatible so neurons feel more relaxed, let's say. And we know that theoretically they can live even 100 years because in our
Mm.
heads during the adulthood we mostly have the same neurons all the time. There are not many places in the brain where they are producing new neurons. So that means that they can live really long with us, even more than 100 years. So we want to also achieve this one day in the lab, but this will require some optimizations. For now, we think for the simple things we do, we think that 3 months is okay. Also because we have
Right.
very efficient process to exchange neurons. So that's also working quite well in the lab.
Right. And Evelina, whenever someone works on something the world has never seen before,
Yes.
there is often resistance, misunderstanding, and personal cost. So, frontier science is never a smooth road. And I
Mhm.
want to explore that human side. What has been the most difficult aspect of working on a scientific frontier?
I think I don't see this difficult. For me, it's a pleasure. I think the biggest challenge is maybe for the founders, for Fred and Martin, because they put their own money on that. And
Mhm.
I think this is the biggest challenge, I would say, because when you spend your own money on something, then you take a risk, and then you might really lose something. So that's a risk. But for everything else is pleasure and fun to do this. So I don't find it difficult. But I also
Right.
don't work. But even if you work in the lab, I think I think we have nice atmosphere and really promoting innovation. So
Yeah.
I think the only challenge here is for the founders that they take this commercial, let's say, this financial risk, and that's
Sure.
I would say is challenging because for the moment we are self-funded,
Hmm.
and this is why we are such a small team, only 6 people, and we are going very slow. But we also talk to investors about potential investment of maybe 50 million Swiss francs, and
Right.
that will accelerate our research. And then maybe someone else will help us to take this risk, this challenge further. So I think I see, like in every startup, the risk is always financial, I would say.
Mhm. Right. Rightly said.
Yes.
And there's a statistic that
Mhm.
shocked me recently. I came across that recently. Some large AI models now use more energy in a single training run than some household use in a year. And the world is reaching a tipping point in computation.
Yes.
And this is where biocomputing becomes more than a scientific curiosity.
Mhm.
So, Evelina, how can biological computation change our relationship with power and cost?
Well, it just will we will be able to provide processors which will use much less energy. So we will have AI which will cost less and use less energy. And actually, there are a lot of ideas in, I would say, in engineering and science on how to use the learnings from human brain for improving AI. To actually even build AI, because artificial neural networks are also inspired in with the living neurons. There is also field like neuromorphic computing, where people try to make some kind of optimizations of
Right.
digital hardware or software or hardware, or even they try to make analog hardware. So it's all in that matter. There is no living neurons, but they try to build something which is closer to brain. So it's more efficient. For example, the time encoding, so that you have spikes. This is more efficient than the 0 1s in digital. So people try a lot. Also, I read recently that actually Jan LeCun, which is one of the fathers of artificial intelligence digital, which we have today, he's actually also believes that he believes in a bit different stuff. It's not biocomputing, but he believes in the new architecture for artificial intelligence digital, which is also actually inspired in human brain, with human brain, and how brain is learning. So for example, that is modular and not like ChatGPT is only one model, huge. So I think there are a lot of things you can find in science and engineering where people try to improve AI, also efficiency, energy efficiency, by learning from brain, which is extremely efficient. And we just put this idea to the extreme to get the maximum. So we just want to use real living neurons, because we believe that this will bring AI, which will be the
Mhm.
most efficient. Because with other things, with neuromorphic computing, you can have maybe a few times more efficiency. But with living neurons, you have 1 million time difference compared to digital computing. So we think that will be the biggest step change in the energy consumption.
Right. And like you said, when we take a step back, the possible applications are enormous.
Yes,
AI, robotics, drug discovery, even neuroscience research. And it feels like we are standing in the lobby of an entirely new industry.
yes, absolutely true.
Yeah. So what real world use cases do you expect to see emerging first?
So we aim for general computing because we
Hmm.
think neurons can analyze any kind of, like, process any kind of information like we in our brains. But we think that the best use case, which is for now in our mind, is generative AI. Actually, everything we assume about biocomputing is based on the human brain, how a brain is working. And based on this, we can conclude that neurons are good in processing efficiently very complex information. So this is what brain is doing very well, and we think that biocomputer will have the same properties, also generating new ideas. We think that this will be perfect task for biocomputing, also because it costs a lot of energy in digital.
Right. And I think about the computers from the past, and the first computers were room sized and
Yes.
unreliable. And yet they evolved into the
Yes.
devices that run our lives today. And biocomputing today feels like the same early moment. So I want to understand what must happen next for it to mature.
We have to learn how to program neurons. So for the moment, our biggest challenge, the next milestone we have in the startup world is called learning in vitro. So we want to figure out how to perform a simple algorithm on living neurons in vitro. So for example, maybe reproduce some logic gates, maybe make them recognize some simple images. And that's the $1 million question now for the nearest future. And later we want, of course, develop advanced algorithm. And after we want to scale also, because now we have very little prototypes. But as I mentioned before, we want to have huge structures of neurons in the future in so-called bioserver. So we hope this is also not easy. We have to figure out, for example, how to provide nutrients to all the neurons because they all need oxygen and nutrients and water, everything. And in the human body, we have vessels, very complex system of vessels, so that every cell is nourished, and we have to kind of figure out the same for the artificial in the lab.
Right.
So this is a big challenge. And nobody knows this yet, and it's a big question also for biomedical research. People try to do this kind of things, but it's difficult. It's called
Right.
vascularization, like how to make vessels, and maybe some artificial things, or maybe induce
Yeah,
biological vessels, but you need to get something so that
exactly.
every cell will get nutrients and oxygen and everything. So that will be
Yeah.
the last challenge.
I think by far that has been the most perplexing piece of the puzzle for me because
Mhm.
I'm just not able to wrap my head around
Yes.
the scenario where we scale up the operations and until we find a sustainable artificial or synthetic way of producing these cells, that
Mhm.
how can we possibly meet the demands when things scale up? And also because the average life is so small that you got to keep replenishing these cells with new ones and sourcing
Yes.
those new ones again. So I think that supply chain is going to be the trickiest part.
No, actually, we don't think so, because the trickiest part is how to learn to program neurons. But actually, you can produce a lot of neurons in the lab. It's easy, and actually, this is also advantage over digital, because you don't need any rare materials. You don't need any complicated manufacturing. I think it's easier to produce living cells than silicon chips. And also, we believe that if we learn how to program them, how to interact with neurons, then if part of the computer will die, we can always replace it. That's assumption.
Okay. And when you replace the part that is dead already, do you need to retrain that part, the new part, or
Yes, definitely. We will have to retrain because they will be fresh neurons. They don't have memory of the previous ones. But
right?
what is important is that neurons are learning in different way, faster than digital. We have some kind of something like a one-shot learning. So this
Hmm.
is also in our brains. When you
Yeah,
see a cat and dog one time in your life, it's enough. You will always know the difference. But computer must see much more examples. So yeah, so we believe that the training will be easier than for a digital computer.
right. And Evelina, I find it helpful to step out of the present moment and look ahead.
Mhm.
Because when you describe your work, it is clear that you are not just thinking about experiments, you are thinking about the future of intelligence itself.
Yes.
So, what does success look like for biocomputing for Final Spark?
So we want to build a biocomputer, a
Hmm.
bioserver, so-called. A bioserver will be central point. Maybe there can be many of them, but the whole
Mm,
point is that it will work the same way like today cloud computing, that you will
right.
be able to connect remotely and use the computing power. And we believe that it will be possible to run algorithm, maybe
Hmm.
the same or similar as on the digital, but it will be much cheaper.
Right.
And considering increasing energy consumption, that will make a difference in the future, because AI is much more expensive than we think. For now, you can use a lot of LLMs, for example, for free or with a low subscription, but these companies are losing money because they still need adoption. People have
Yes.
to get used to, and also models have to improve. For example, OpenAI, they lost around 19 billion, so they are
Oh,
not profitable at
okay.
the moment. So that means that ChatGPT and other things has to be actually much more expensive to make it profitable. So we believe that biocomputing will make a huge difference because biocomputing will be real cheap computing, not just
Right.
lowering the prices to get adoption. And that's also great for investors because it will be very profitable business. We expect we have made some calculation based on how much it costs today to run the lab and how much we can produce. And based on that, we expect that once the biocomputer is working, it can make a billion of profit, not
Right.
even the revenue, but pure profit.
And there's another question that I have. For instance, neurons that are derived from the human body or from
Yes.
a living body versus those neurons that are developed in petri dishes or in the lab. Is there a difference in the quality of their ability to process and learn information?
Yes. If you want to go really into details, yes, there are differences. Actually, there is still discussion in the scientific community. Some neuroscientists believe that it's not the same. They think that the neurons which you get from stem cells in the lab, they are like infant neurons, kind of, like
Mm,
adult. And also, we have done actually some RNA analysis, which is also the data are on our website. So we check which receptors, because every cell has receptors on the
yeah.
surface, on the membrane, so that it kind of like decides about the type of the cells, and because the receptors will decide to which stimulus you can be sensitive. So
Mhm.
we actually did a lot of big analysis of that. And yes, our neurons are still missing some elements, let's say. But also it's not clear what does it really mean, the right neuron, healthy neuron, which type of neuron, because in the brain you have many different type of neurons. So actually that's part of the challenge. Which kind of neurons do we need to make a biocomputer?
Mm,
And to which extent it has to be perfect, which receptors do you need? So we play with different cell types, for example, with different neuron types. We try to
right.
combine them, but you can say for today, I think that it's not the same when you take neurons from stem cells and if you look at those which are in the brains. It's not exactly the same, but very similar.
Right. Okay. And after everything you've worked on, there must be
Yes.
moments that stand out for you, moments that made the struggle or the uncertainty feel worth it. So, which breakthrough or moments fill you with the most pride?
I have to say again that it's not such a struggle. Actually, I enjoy a lot the work which I do, and I really like it. So it's not that I have struggle. Maybe when I was in the lab, it was a little bit more difficult. Although I also really loved that. I just at some point I had enough, but but I really enjoyed being in the lab. I think that when you publish something, it's always a pleasure. And
Mm.
when you publish scientific paper, it doesn't happen a lot because you have to work a lot to get some paper, and this is really nice. Although I have to say that I always choose to do stuff which I really enjoy on the daily basis, because I think if you only work for the reward, then you don't, then it's not worth it, because still on the daily basis you have to do this all the time. So for me, it's important that I enjoy every day, not just that something happens sometimes. So yes. But I always enjoy when we make publication. We also did a scientific publication with Final Spark. So
Hmm.
I'm very proud of this because this is engineering paper. I've never had it in my career, kind of, because it's very, very technical paper on how we build the lab and how it works. And this paper is top 1% in journal
Wow.
Frontiers, in how many people read it. So we are very proud, very happy with that. And also because we talk a lot with journalists and podcasters. Actually,
Hmm.
now I publish all the time something because there are so many things from the conversations. And this is also nice. It's a really pleasure. It's just giving some output to the world. It's
Yeah.
always a pleasure. If it's scientific paper or maybe some podcast, I think it's always a pleasure when you see some kind of results of your work
Yeah.
going outside to the world. It's always nice.
Yeah. And I think this science is so fascinating that I have so many questions. I can just go on. I can just go on. And it's fascinating to think about. Just a few years ago, we were saying that human bodies they'll become hybrid bodies. They will
Yes.
integrate with technology. And now we are saying that technology will actually become a humanoid. So
Yes,
it's
this is very funny to see how these borders between human and technology are changing.
merging, blurring boundaries. Yeah. So, Evelina, there'll be people listening who are curious, inspired, and
Mhm.
even unsettled by this conversation. many will wonder how they can get involved or learn more about this. So, if someone wants to explore biocomputing, what should they do tomorrow?
I think a good idea is to go to our website, finalspark.com. You can also join our Discord channel. The link is also on the website. You can also send us a message. It's very easy to contact us. We have a lot of forms for researchers, for investor, for press, also for media on the website, and we answer every message. And we give some reading materials about biocomputing. There are no books. Some people already ask me, but to my knowledge, there is not really a book about biocomputing. You can find a lot about maybe how neurons process signals, but that's not really the same. Maybe like biocomputing, because really biocomputing is just burning now in front of our eyes. So there is not a lot. There is a lot of literature about neurons and maybe the biology of neurons, but not so much about biocomputing. Is very new field. So I think, yes, joining the Discord and sending us message is a good idea to start. And reading our paper also in Frontiers, if someone would like to have some ideas on maybe what they can do with our lab today.
And
That's
maybe I
also
can
interesting, because
include,
that's real actually work on biocomputing you can do if you have some ideas.
sure. And I'd be happy to include all the links in the comments so
Yes,
people can find it very easily, including your
absolutely.
website, any
Yes,
publications, any papers, and your LinkedIn. I'll tag you anywhere so people can find you.
yes.
And Evelina, I always like to end by zooming out.
Mhm.
So beyond the experiments, beyond the technology, beyond the science, to the deeper meaning behind your work, what do you hope your work ultimately teaches humanity about intelligence and life?
Well, I always want to make the world a better place, so I think that's always my objective. I want to do something what will have a positive impact, of course, because that's otherwise why would you do anything? So I think for me the only thing is important that to have a positive impact, and I think it's collective. It's not only me or some person.
Mm,
But I think we do this together like a whole generation, and I think the goal is that next generation will have easier life than the previous one.
yeah,
So I think that's a good thing if this will happen.
right. That's fantastic. And that brings us to the end of our today's conversation. Evelina,
Thank you so
thank you
much.
so much. Thank you
Thank you.
so much for your time and for sharing the insights. And what you and the team at Final Spark are building is one of those rare moments in science where the future becomes visible a little earlier than expected. You have taken us inside a world that most people have never seen, never imagined, and certainly never thought they would be able to interact with. And you've also shown us that intelligence is not limited to machines, that computation does not have to mean silicon, and that biology still holds mysteries and capabilities we're only beginning to understand. More than that, you've helped us see the care, the ethics, and the intention behind this work, which matters just as much as the science itself. So, thank you so much for your clarity, your humility, your willingness to bring this emerging field to a global audience. So, thank you so much for joining us today.
Thank you too. It was really a pleasure. Thank you.